Welcome to I Can Science That. We've been doing a lot of talk about relative density in the Science for Skeptics section. But this video is related to those. This one's more targeted towards the science folks. So this is more like skepticism for scientists. When we look at the concept of relative density as a replacement for gravity, it's really easy to just dismiss that and say these people don't know what they're talking about and just go on. But as I've been trying to reach out to the skeptic community and show them a formula that embraces the role of density in the downward weight or the buoyancy of objects, it's really become very clear to me that the concept that relative density governs the way things move is even more right than I had previously understood. So if you're a skeptic and you're interested in this concept, maybe give this a try, give this a listen. There's going to be a lot of math though. This is a mathematical analysis meant to show to the science crowd how simply rearranging the math can reveal to us maybe a little bit of what those skeptics have been trying to say this whole time. If you haven't seen it, this is what I call the law of relative density. The purpose of this formula is to try to bring together the science and the skeptic. The skeptic who says it's not gravity, it's density, can look at this formula and we can all agree density is right here. And it has to do with the difference between the density of the object and the density of the medium it's in. That absolutely governs the motion of the objects. Now, for the science folks, though, you'll look over here and you'll find that there is a downward acceleration term that is on here that describes how the object will move in response to its density. So this is what I keep talking about, is the bringing together, because both sides are actually kind of right. The relative density folks are insistent that density has something to do with this. And shouting at them that no, it's not density is counterproductive and technically wrong, because density is sitting right there. If we just agree to call that the relative density, that's what I've been doing, call that the relative density, then yes, density is a dominant factor in whether something floats or sinks and how hard it floats or sinks. Now, if I just factor this expression out, I'll get to something that looks more familiar. The density times the volume of an object is just the mass of an object. And so I've just factored that out right here. And so this is the same equation, just having factored out the K and the volume, and then turned the density times volume into the mass. I get this question all the time from science folks. They go, hold everything, why isn't gravity in there? So they want to insist that gravity is the reason for all of this. Right. Remember when I said there's a universal natural downward acceleration term that I've expressed right here? You would know that as the gravity term. If you're a skeptic and you're following along with this, this is the gravity term. That is what the science folks call that term. Throughout the course of this series, we have done nothing to evaluate whether this is mass attracting mass, or is this the bending of space-time, or is this just some natural phenomenon that is related to density? We have not explored that yet, and so I have been using the generic K letter to keep us away from any assumption that it is gravity. But for the science folks who are more comfortable talking about gravity, let's embrace that for them for this video. And that is this equation here, which you may recognize as the weight of the object and the buoyancy of the object. This is just the weight, this is just the buoyancy term, and those should be the exact same formulas that you recognize from your old physics textbooks. All I have done with this one is rearrange it to highlight the role of the difference in density in the overall behavior. Rather than dealing strictly with forces, many people have suggested we should be talking about accelerations. Now, I have stayed away from that for the Science for Skeptics series, specifically because it adds additional complication. You cannot measure acceleration unless you're moving through the medium, and now drag is going to be a term that's going to add additional complications and has historically notoriously confused the subject. But for our purposes, let's take a look at this and see where that leads us. Here's our original equation, copied from the previous slide, and I want not force, but I want acceleration. To get there, I will use our old standby, F equals ma. So I'm simply going to replace force in this expression with mass times acceleration. I've got mass on both sides of the equation here, so I'm going to divide that out. So now I have the acceleration all alone, and over here I have the rest of the expression. Now, mass divided by mass, I'll cancel those out, and so those can go. And over here, I'm going to replace mass with density times volume. I'll do that so that I can drop the volumes. And now I've got this expression. The initial acceleration is this term. Let's go ahead and factor out that g. And lo and behold, look what we've got. This expression right here is that ratio. Our friend from the relative density camp insists must be this ratio. He wants it upside down, but I've seen him concede that this order is okay. Well, look at that. So if you are in the skeptic community and you have been waiting for someone to finally say, look at this, it's all about the relative density, and even if you insist the relative density must be a ratio, take a look at this. This is an equation that the science nerds, including myself, will embrace and agree with. All we got to do is argue over this g now, and maybe insert that k back in there and insist we have not proven the source of that vector. Only thing we have proven is that it exists. And yeah, if you still aren't on board with that, then that's an argument that we have to continue until we both understand why that term has to be there. For those of you who are in the science camp, take a look at this expression. When I wrote this the first time, I was shocked at how little attention people had been paying to the fact that it's sitting right there. When people insist the downward motion is due to density, it's due to density, we don't need to shout at them and tell them, no, it's not, no, it's not. It is. It is due to density. Here it is right here. It's also due to gravity, which is also here in the expression. We need both. We can't explain the behaviors of objects unless we have the density and the gravity. We need both of those terms. We should not be telling them no on the density, on the relative density. We should absolutely be telling them, yes, you're right, but you need the other term also. You need both. Okay, and we should all be agreeing that this is the case. Although, this came up in discussion last week, and the shocking thing was, hold the phone. I remember from physics class that the acceleration of any object is just g. All objects, when dropped, accelerate downward at 9.8 meters per second squared. It's drilled into our heads. We learned that in physics. That is not what this expression here says. That would only be true if we assume the density of our medium is 0, which is what we did in physics class. Remember, in physics class, we would start off with the simplification that we will neglect. We're neglecting friction all the time. We're going to neglect aerodynamic drag. And yes, we're going to just neglect buoyancy for most of the time. And why is that? Because you drop a steel ball through the air, how much buoyancy does that have? It's so small, it's not a significant figure, right? So we normally just drop that and don't worry about it. But it's there. And why it's so important is because the skeptical people, the gravity is not real folks, are insisting that it is related to density, and they are expressing that, they are showing that through buoyancy, buoyant objects, helium balloons. If you try to neglect the density of the medium using a helium balloon, that would fall down in your face. Helium balloons do not accelerate downward at 9.8 meters per second squared. We all understand this, we know this. Now, roll back into your mind here. You need to take a pause. Some of you, some of my subscribers are just fantastic at math and physics and can teach me things about this, and then turn it inside out and left and right and sideways. I know who you guys are. Some of you, though, are very into science, but are being shocked right now by the fact that acceleration is not just g. No, it is not. Science does not teach that acceleration equals gravity. That's only true if we neglect the density of the medium that you're in. Here's the initial acceleration. And I do call it initial. I call it initial acceleration because I am still neglecting aerodynamic terms. And I can get away with that if I say the initial acceleration. So the object is not moving. I just have an object in a medium and I drop it. At the moment I drop it, its velocity is 0, the airspeed is 0, and so the aerodynamic drag is 0. So only for that instant is that going to be accurate. Once the object starts to move, we need to add the drag term, and perhaps we'll do that in the next video if people are interested in that. This is what we did in physics class. We said weight is mass times gravity. In my earlier videos, I was saying that I wanted to call that net force term that included buoyancy, I wanted to call that weight. And I got a lot of pushback, particularly from the science folks, but even from the skeptics as well. People did not understand because they were certain that weight meant mass times gravity. So I'll not fight that. Let's say weight is mass times gravity. Great. And then old standby F equals ma. Put those together and what do you get? But acceleration should be weight divided by mass. When we did this in physics class the first time, we then said just put in the weight is the force acting on the thing. So that's the F. We'll just replace the F with the weight. And acceleration is force divided by mass. That takes us right here. And now let's just put in that the weight is mass times gravity from right there. And what do we get? Boom, the masses drop out. We all did this in physics class in high school. The mass drops out and you get acceleration equals g. That is what we did. And it does not match. It does not match this equation here. It's very close. Where did we screw it up? Were they lying to us in physics class? Now, I'm going to explain it, and those of us who have a good relationship with science are going to accept that, or probably already have by the time I get the words out of my mouth. Those of us who are skeptical, they see this and they say, you lied to me. This was a lie. You taught me this. Mr. Teacher, you taught me this in high school. And now you're saying this. So you lied to me. You've been lying to me this whole time. Now the answer I say is, no, I wasn't lying. We were not lying when we did this. This was us neglecting this term. We just said we wanted to make it simpler, so we didn't cover that yet. We cover weight, we cover gravity, we cover acceleration and forces well before we get into buoyancy. Buoyancy is going to come later. And so we don't introduce this term at this time. And so we do this derivation. You go along here and you do this and you get this term. And we talk about Galileo now. And we say Galileo said that when you drop two bodies of different masses, they should fall and hit the ground at the same time. And everyone told him, no, this is heresy. But he went to the Tower of Pisa and he did it supposedly. I don't know if this is even true, but we tell the story. And we drop the balls and then boom, and they land at the same time. Ha ha, proof. And I was just talking to somebody. I was talking to Rob Parks in the chat last week, and he said, "Yeah, isn't that right?" And I was like, "Well, no." and he said, "Well, hold on now. I heard the relative density folks say that. The skeptical folks said that this is not true. They said less dense objects really do fall slower." And Rob was like, no, they don't. Because he remembered, like I do, this equation from high school physics class that we learned, that this derivation where we proved that mass drops out of the equation. Only what we didn't learn at the time, and perhaps never put those pieces together since, was that this is making the assumption right here, this F equals ma. I just replaced the F with the weight. I just said the weight is the force. I said the weight is the force acting on that mass. But it's not. Right? That's not the whole force. What are the other forces acting on that mass? We need to add those two. So we need to add aerodynamic drag, which I've said let's neglect. And we need to add buoyancy, which back in physics class we said let's neglect that. We'll say it's very, very small, so small we don't need to worry about it. But when you say that to a skeptic and they see now something that is not true, you throw at them everything dropped must accelerate at the same speed, and they catch that and they see that and they say, no, they don't. They do not. And in fact, I had this very discussion with Rob this week, and that highlighted to me that they have a legitimate point and they have a legitimate complaint, which is that we learned this and many of us have simply accepted it without question and just ingrained it, and dare I use the word indoctrinated. We've been indoctrinated to believe this equation when technically it's not complete. It's a simplification that discounts density. And so as soon as somebody says, well, hold on, what if I drop a cork and a lead ball at the same time? Are they going to accelerate at the same rate? Most of us, I think, would say yes. Most of us would say yes, because this is the equation. With a lead ball in the air, yeah, I could discount that. It's not going to do anything. What about cork? Is cork dense enough that this ratio is going to drop to nothing? How about a balloon? Let's take an air balloon. Now an air balloon is denser than the air, so it's going to drop. But can we neglect that term? No, we better not be neglecting that term if we drop an air balloon. So if you drop an air balloon and you drop a lead ball in the air and you measure their initial acceleration, you're going to see the lead ball accelerates at about 9.8 and the balloon accelerates very, very slowly, right? Put in something lighter than air, put a helium balloon, and it doesn't even accelerate down, it goes up. So that brings me to the next question that has been a lot of trouble for us on the science side. What is weight? I started us off trying to use the operational definition of weight, where I said, hey, the weight is just whatever the number on the scale says. Let's take a look a little deeper at what exactly is this thing. What is this thing here? That is a scale, or sometimes called a spring scale, in order to really differentiate it from a balance. Right? And the balance, we'll get to that in a second. A scale is when you just, and what is that? It means it has a spring, right? And you're gonna, or it has a spring, or I say here an analogous structure. It may not be literally a coil. It is something that is compressed when you push on it. And we're going to put a little strain gauge on that. We're going to measure how much compression we get. So it's, you know, maybe it's not literally a coil. Sometimes they are literally a coil, right? You just get a cheap, like a fish scale or a supermarket scale. You see them in the supermarket. You get your bananas and you put your bananas on the scale, and there's just a spring in there, and you pull the weight of the bananas pulls down on the spring, and how much spring stretch indicates the amount of force that we're doing there. That's all it is. It just measures, even this thing, this digital scale, it has something in there that gets compressed, and there's a strain gauge on it, right? So we measure how much compression it's feeling. That's all that is. So what is this thing measuring, right? This is measuring the net force, the total force, whatever force is acting between those two surfaces, whatever is pushing down on the scale, whatever that is. So obviously that includes the weight of the mass, the gravity-induced weight of the mass, but also buoyancy. If there's a buoyancy effect, that is going in there as well. If you are accelerating the whole thing, the reaction force from that acceleration is included there. If there's an electrostatic force acting, that will be included. I'm going to say, obviously, the objects are not moving, so there shouldn't be any aerodynamic drag, I would think. But you know what? If you had this in a wind tunnel and there was air blowing, the wind would induce a force on there, absolutely. So this thing just measures the net force acting on it. And in our cases, I think we've agreed that what we're talking about, we have to include weight, and we have to include buoyancy. So what is this thing measuring? I don't know. It's measuring net force. And if you don't want to call that weight, we'll just call it net force, but we'll agree buoyancy is going to matter for these discussions. Okay, here's the equation. Again, from the previous slides, of what this thing is measuring. It is measuring the term that you recognize as the gravitational weight. Yes, that is included, but also here is the buoyancy term, the mass times gravity times the ratio of the densities, and it acts in the opposite direction. So this whole expression is what this thing weighs. Okay, so is that weight? When you put something on a scale, do you get the weight? Well, if you've defined weight to be mass times gravity, then no, you do not. Do you get the mass? No, and we all remember it was emphasized to us in physics class that the spring scale does not give us mass. Why not? Because gravity is multiplied on there, they said. And now I'm saying, and also, by the way, the density ratio, the buoyancy term is on there too. And this brings us to a trick question, a little trick question. We all remember the old joke, which weighs more? Which weighs more, a kilogram of lead or a kilogram of feathers? Which weighs more? And then the joke is, haha, they weigh the same. Because a kilogram weighs a kilogram weighs a kilogram. And no, not well. Well, it depends on how you define weight. If you define weight as mass times gravity, then yeah, they weigh the same. If you put them on a scale, no, they will not be the same, because this term will be different for those two masses, and this scale includes that. So on that type of scale, you will find that a kilogram of lead weighs more than a kilogram of feathers because the feathers are more buoyant. They have less density. We'll fix it. We'll fix it. We say you should not use a scale to measure mass. We're going to measure mass with this thing. This is a balance. And the way this thing works is we put weights, masses on both sides. We put a mass over here, and then we take these reference masses here and put them over here. And now we can add up. When they balance, we know that we have the same mass on both sides. So here's the balance. It's different because it doesn't use the spring. The scale, the spring scale, uses a spring. It's based on Hooke's law. This is not, there doesn't need to be any springs in this at all. It's comparing the weight of both objects. And I think they taught us, the way I remember hearing this, it was, it was 9th grade. It was a long time ago. But the way I remember this story going, this thing is going to measure your mass, not your weight. And they would emphasize this thing will work on the moon. Like if you go up to the moon, your scale is going to be all out of calibration. It will no longer be able to measure mass because it measures weight. That's what they taught us, was that the spring scale measured weight and the balance measured mass, right? But is that true? Now that we're talking about buoyancy, I think we need to look at this a little closer. So here's my little diagram. Here's my little balance. I'm going to put a mass on one side, and it's going to have a force. It's going to have a downward force. So this is force number 1. And here's the equation for force number 1 that, going back to my old form there. It's the same equation. You can rearrange the terms any way you want. Okay, here's a different mass, different volume, different density. It's a whole different thing, right? Because it's like we're measuring like bananas on the one side and we're using our reference masses on the other side. So it has a downward force. And there's the equation for that one with the different density and the different volume. Okay, now when we've balanced our balance, the point is that the two forces are equal. So we're going to set those equal, and the gravities cancel out. There's gravity on both sides. I'll just drop those out. And so now we've got this. What am I doing here? I'm just going to distribute out. Just going to distribute the volumes across so I can drop the parentheses. That's all that is. What am I doing here? I just want to arrange the mass of object number 1 to be in this term like it is in this term. And so I'm just going to multiply by row 1 over row 1, right? So I'm not doing anything here. This is just row 1 over row 1. I'm doing that so that I can take this row 1 V1 and make that M1, and this row 1 V1, make that M1. I did the same thing over here. I just did that so that I could get the masses out. Okay, here's that equation again. Let's factor out the masses. So here's M1 factored out and M2 factored out. Now, thinking back to 9th grade physics class, or whenever you took this physics class, and they said the balance measured mass because we set our mass equal to the reference mass. But I think we see when we look at the actual equation, now that we've included buoyancy, we did no such thing. We did not measure the mass. We measured this term, which includes the buoyancy factor. And just for reference, here it is once again. This is the term that I started with, that I said, or this is our term that includes the gravitational weight and also the buoyancy. So that's the term I had been calling weight, which now we'll just call net force, I suppose. So what the balance did was not measure mass. The balance measured the net weight. It did not say these sides have the same mass. It said besides have the same net force. So on the moon, yes, you will get the mass, because on the moon the density of the medium is 0 or even closer to 0, and it's still not 0, right? But so close to 0 that even a helium balloon, right, won't matter. But here on Earth, we're going to need the density of air for that. And if we're talking about applying this type of mathematics to other mediums besides just air, we could get some significantly important buoyant factors. We've all seen the anvil floating in mercury example. That would not have worked if we had discounted this density. So let's wrap it all up. Here's my original law of relative density. And if you'd rather see it in this form, I've changed out the K to the G and factored out that mass. And now it looks like this. And you've got a ratio of densities in the equation. This is the exact same formula. I accept both. They work exactly the same. Those formulas work great. And you want to know acceleration. Now that we've included the buoyancy term, look at that. The acceleration is not just 9.8 meters per second squared, not here in the air. If you're in a medium that has a density other than 0 and you want to include that term, that is what the initial acceleration looks like. Let me know if you want to talk about aerodynamic drag and how that's going to affect the thing. If you actually want to do this as an experiment, you're going to have objects moving through the air and you're going to need to include drag. And we could talk about that if you think that's interesting. For the skeptics out there, the biggest takeaway I want you to have is that back in physics class, when they told you everything accelerates down at the same speed, and you insisted in the comments of somebody's YouTube video, you insisted, no, they don't. Lighter objects really do accelerate downward slower than heavy objects. I just know that they do. You were right. Yes, if you include the buoyancy term, the lighter objects are going to accelerate slower than the dense objects. They will. And if you include the drag term, the effect becomes much more dramatic, and we're going to get even more slowdown in the medium because of aerodynamic drag. Now, for all those science people who banged out into the comments, no, it doesn't. Everything falls at the same speed. Let's pump the brakes, guys. We are on the side of science. We are on the side of reality, and that means we are flexible. We are going to remain open-minded to what reality actually is, and constantly keep ourselves open to, hey, have I missed something here? And so no hate comments. If somebody says light objects fall slower than dense objects, we can say, well, you know, a little bit, a little bit. It depends on the density of the medium. It depends on the density of the object. If you're talking about lead versus iron, I mean, in the air, nah, I mean, it's a little bit different. I mean, it's too small to care. But if we're talking about, I don't know, like a lead versus a balloon, then they will be absolutely different. And the person who claimed that they were different is correct. Let's ease off on that. So there you go. That's relative density, more right than you may have given it credit for all along. Let me know if you guys want to talk about drag or something. What I'd really like to talk about next is this K term, or is it a G term? Where does that come from? If there are any skeptics out there still watching, I want to get to where we can agree that this term here, whether it be called G or whether it be called K, needs to be there to explain the results that we see in nature. And we can't do it without it. We have no replacement for it that has been offered from the relative density crowd, none that works. So I want to get to the place where we can talk about why this term is here, why it must be there, and then investigate what the cause in nature is that generates that term. That's where I'd like to go. Looking forward to that. Looking forward to your comments, and see you out there.